The Rockies are right over there. Don't just go to the conference. Go and see the Rocky Mountain National Park. Go hiking up at Bear Lake or something. Don't do what I did, which is just to come for the conference. Go and see the area.
Good morning. Welcome to the Back to Basics track at CppCon. This conference track is about all the things that all C++ programmers ought to know about, all the basics. So we're going to talk about the basics of unit testing. Well, we're going to try. Okay, it turns out that that's hard or impossible for about 3 different reasons. First of all, not everybody agrees on what a unit test is. We'll have to work that out. Secondly, it's a new area, new for the software community as a whole, so we're still learning about it. And third, the one thing we know about it is that it's too big to talk about in one talk. But we'll see what we can do. So first of all, whoops, Wikipedia, don't read Wikipedia's. I put this up there only to point out all the weasel words and equivocations, right? It usually corresponds to, it may imply or may not be a function or a module or a method, or it might not be, right? Like, so this is actually technically correct, but it's just not actually very useful. The definition we're going to use that C++ developers and really all actual software developers use is much more specific. Unit testing is testing your code at the smallest possible unit you can execute, which is the individual function, more or less. We'll have to fix this up later. So at least we can clear that up and we know what we're talking about, but you will find a lot of other terminology used in other parts of the software industry, or the term unit test gets reused. Now, I mentioned that this was kind of new. 20 years ago, this was a thing some people knew about and said, hey, that's really cool, we should do that. Maybe a decade ago, it was a lot of people are saying that's really important and everyone ought to do it. Where we are today is it's a fundamental part of software development. Developing software without unit tests is unthinkable, and any project that isn't doing unit tests is almost certainly going to fail. That's where we are now. But it's still new and we're still learning about it. And then the third problem is that it's really big. If you ask Google how many YouTube videos there are about C++ unit testing, it'll give you an answer somewhere north of 700,000. I'm not totally sure I believe that, but it's big. Look at it this way. Just this week, we've got at least these 5 talks. There might be another one I haven't noticed. All right? Jody Hagen's later today about design will actually touch on that. And you'll have to take my word for the fact that Pete's talk is about unit testing. I don't even have time to explain why, but it is. And that's just this conference this week. There are dozens and dozens and dozens of books and hundreds of conference talks, and you cannot count all the blog posts about unit testing. And the thing you will find is every one of them will give you a slightly different list of the basics. Not that we disagree, right? I mean, everyone who does this kind of knows what's going on. Everybody's got a different list of what they think is important because they're solving different problems or taking a different approach. So given all that, what the heck are we going to do? So over the next hour, we're going to take a whirlwind tour through unit testing. We're going to try to get a lay of the landscape, note all the big important things, dive into a couple of areas. But I can't tell you all the basics because A, I'm not sure I or anyone else actually knows them, and B, I don't have time. I can't even mention them all. So I'm not going to teach you everything about unit testing. I'm going to do the next best thing, or maybe better. I'm going to show you how to learn it. How do you approach this big, complicated, evolving topic? How do you learn this? So as you go to all these other talks, you know what people are talking about, and you know how to handle all the information you're going to get. We're going to talk about the basics as we know them now, but we're also going to talk about how they fit together. So we're going to cover a lot of ground here very quickly. And there's going to be a lot of references and links in these slides, which hopefully you get, I don't know, later today or later this week, so that you can go dig into whatever areas of this you need to dig into. And here's the first. This is maybe the first really important talk that went up on unit testing from almost a decade back. This is Hiram Wright and Titus Winters. This has set the stage for a lot of discussion that's come afterwards. Gets quoted everywhere, usually without attribution. I'm going to attribute this, and I'm going to start by making a point they made just much more loudly. All right? The first rule of unit testing, because we're C++ developers and we know how to index, the first rule of unit testing is that you must write unit tests. We are going to talk a lot about what makes a good unit test, and there's a lot there. But even if you can't do all that, or you don't understand it, or whatever else, you have to write unit tests. Testing software is a defense in-depth strategy. There's all kinds of different tests, many of which are called unit tests, which is confusing. But you've got component tests, subsystem tests, system tests, integration tests, smoke tests, soak tests, all this stuff. And these are all layers that we put between you writing your code and something getting out to the customer and going into production. And the idea is at some point along there, any given bug has a very high likelihood of getting stopped. Unit testing is the first line of defense. So it's important. That's why we're here. But you don't have to catch everything in your unit test. Turns out you can't. And even partial unit tests that are imperfect are incredibly valuable. So even if you can't do all the things we're going to talk about, you have to write unit tests. Now, we're going to spend just a little bit of time on the real basics of the basics. What the heck are these things? I put up, or at least temporary definition a minute ago. We are testing at the level of individual functions, because in C++ you can't call half a function. That's unit testing, the verb. Unit tests, the things, are small, automated, standalone executables that perform the unit testing on your code. Now, all of those words are important. There's a lot to unpack, and there's a lot of abstract stuff here. So let's actually put some code up and look at it. Here's the code we're going to unit test. We're going to take the absolute value of an integer. Frequently, this will be called the code under test or the system under test, the terminology that gets used. And our first cut at a unit test might be something like this. Now, it's not a great unit test, but remember the first rule, it's a heck of a lot better than nothing. There are things we don't like about this that we'll make better. You might wonder if this is complete. Do we need to put more stuff? We'll come back to that. There are some kind of even more basic problems with this, things we'd like to avoid. The first is that, well, first of all, keep in mind that this main is not the main of your thing, your game, your service, whatever, right? That's your production code. This is a separate file that gets compiled into a separate executable which runs and tells you, right? As written, if this doesn't encounter any errors, it produces no output, which is exactly the same thing it does if it didn't actually run any tests. We would really like to have a positive signal that our tests actually ran. Now, the second problem is how it actually tells us about things. Let's put a mistake up, right? We let an extra negative slide in. So now line 5, the assertion on line 5 is going to trip. And when it does, the output isn't bad. I mean, it's certainly visible. And it points us at the right line, right? It's on line 5, and it tells us what's there, but that's it. We can do better, and we need to do better. I'll show you how to do that in a minute. The biggest problem, though, is that if the assertion on line 5 trips, the assertion on line 6 never gets run. This only runs up to the first failure. We always want our unit tests to run everything and tell us all the things that are wrong. So it's not a great unit test. It's easy to fix, though. What we always do is use a unit test framework, which is just a fancy library with a bunch of engines and machinery that help us do this stuff. Now, there's a bunch of them out there. I'm going to use one called Catch2, originally written by Phil Nash, around here somewhere. He has given any number of talks at this conference and other conferences, so it's easy to go find a talk by him on how to use this. We're not going to dig too deeply into it, but all the examples are going to use the Catch2 unit test framework. So when we do that, here's a more realistic sort of layout of what we're talking about. Somewhere in your code, you're going to have a header file right, which declares your function. You're going to have a .cpp file which defines it. There's the code under test. And now our unit test looks like this thing over here. So you can see on line 1, we're pound including something out of the library. Line 2, we pound include our own code. And then there's this, what is this test case thing? Well, this is the machinery that the library brings to bear. This machinery eventually boils down to a function. In between the curly braces, we are writing just a free function. It's just a normal function. We don't know what its name is, and we don't care. All this machinery registers that with main, which is provided by the framework. It's out there somewhere. And all this machinery arranges for main to know to call this and not die if it crashes, all this other stuff. And then those checks are just fancier versions of that assert macro, which give us a lot of nice information without actually stopping the program. Point of terminology, test cases are generally, I'm going to be a little sloppy about this, they test one thing. About the code under test, we'll make that precise later. And all the test cases that test whatever it is you're trying to test, the code of the system under test, are referred to as the test suite. That's just terminology. But let's get back to what this actually does. What does this do for us? If we compile this into a separate executable, which we can do because main is provided elsewhere, and we run it, we get this nice, clean, simple output that says, yes, I ran your tests and no, nothing went wrong. So that handles the first problem, right? We get positive signal that it did what it's supposed to do. It ran some tests. If we put that mistake back in, now we get some very nice output. If you dig through all this, you get the file and line number of the test case that failed, the name of the test case that failed, the file and line number of the check or the assertion that failed, what that assertion was, and if you look down there around about line 16, it actually expands the expression and shows you what happened. All right? This is what we're after. When we run unit tests, we want to get a maximum amount of clear, concise, and useful information very quickly. We'll talk about why a little later. But this is what we want. So the point is that you always use a good unit test framework, and it's worth spending some time learning how to use it well, learning how to let it help you write good tests, and giving you good output when it finds something. Now I want to spend just a minute talking about the care and feeding of these beasts. Where does this stuff live? And the point is that it lives in your project. It isn't way over there someplace. It's as close to the code it's testing as you can put it. Now, sometimes they'll all just live right next to each other. You've got your project, all your source code is in your source directory, you've got the usual stuff and things that everyone's got in their project, and you've got your math directory, and all three of these files live right next to each other. Cool? The furthest they should ever be apart is something like this, where all your production code is under source, and maybe all of your test stuff lives in a parallel directory structure right next to it. The project I run at my company does it like this for a variety of tooling reasons. That's fine, but no further away. It doesn't live in another repo. It doesn't live over there. It lives with your code. As your code evolves and changes and adapts to new things, your unit tests are right there with it. They live together. So whoops. There we go. There we go. So to wrap up, the very basics of the basics, we have our basic definitions. We know to use unit test frameworks. Unit tests are the first line, not the only line, but the first line of defense against bugs making it out into production, and they live with our code. And so before we dive into all the more complicated stuff, I just want to reiterate the first rule of unit testing is that you have to write unit tests. That's the one thing I want you to come out of here. I want this to be graven on your soul. You are going to go write unit tests. So now let's get into some of the larger issues with the basics. Having talked about this, let's dive into the bigger questions of what makes a good unit test. How do we make good unit tests? And all the advice you'll see out there, all right, most of it, is going to fall into one of three areas. These are maybe the domains of unit testing. And one of them is that we need our tests to be good at testing our code, right? Otherwise, we're sort of missing the point. Secondly, our unit tests are code in and of themselves. The code needs to be good. That means a different thing for unit tests than it means for your normal code. And then thirdly, this red thing is a little fuzzier. How do unit tests fit into the way we do our jobs on a daily basis? How does this affect the way we write code? How do the way we write unit tests affect our code and the other way around? So we'll dive into this first one. We'll spend the most time on this one. We approach unit testing like scientists approach lab experiments. Scientists do experiments to examine the behavior of some aspect of reality. We write unit tests to examine some aspect of our code, which is to say, is it doing what it's supposed to do? Now, scientists have been doing this for a long time, 350 years depending on how you count. And they've developed a lot of deep philosophy about how you do this and a lot of powerful techniques for doing a good job of building lab experiments. We are going to steal the scientific method wholesale. And we can do that because unit testing in science rest on the same philosophical bedrock, which is falsifiability. So when Dijkstra, who introduced the term structured code, right, the first time anyone said spaghetti code was a bad idea, he wrote the famous paper, Go To Considered Harmful. That Dijkstra says that program testing can show the presence of bugs but never their absence. He's basically saying the same thing that Karl Popper said back in the 1930s when he had to rework the fundamental principles of science to deal with a bunch of new physics that had shown up, which is that we cannot prove our stuff true. All we can do is prove it false. Or specifically, what we do is we try to prove it false, and if we fail, it might be right. And the degree to which we think our code is correct is precisely the degree to which we have tried to prove it false and not been able to. So the point is, we are always making falsifiable hypotheses. That sounds very abstract, but it's going to keep coming back. All right, let's get into the details. The list of things that make a good science experiment are long and complicated, and if you were all experienced scientists, I wouldn't have to tell you about this, but we'll dive into a couple of these. We can't dive into all of them. Everything a scientist does to make a good science experiment has an equivalent in unit testing. Everything anyone tells you to do to make unit tests good at testing, some scientist is doing that in a lab in some way or another. So let's take a look at these first two, which are pretty easy. It's the fundamentals of science is that whatever you do, you can do again. Repeatable means you get the same thing every time you run your tests. Replicable means everybody else gets the same thing. So it runs on my machine is not an excuse. Now, I talked about this a lot several years ago, the first half of this talk, back from 21. So you can go look at that. We talk much more in detail about how to handle flaky tests, non-deterministic tests, largely inspired by a conversation I had with Pete Muldoon about a test they had at Bloomberg that failed, what, about 3 out of every 10,000 runs or something? It was driving you guys crazy at the time, right? These happen. It's a common problem. Oops. There we go. All right, let's move on to precision and accuracy. In colloquial English, these mean about the same thing. But in science, we're much more careful about these. Accuracy means something about whether your experiment is giving you the right answer, whatever right means, whereas precision is something more about how much information you get out of the experiment. Now, I spent a whole talk a couple of years ago called It's a Bug Hunt on this, so you can go look at that if you want to go into more detail. We're going to take a real quick view through all of that material. Precision for unit tests is more or less a measure of how fast can you go from, I just found a problem because a test fails, to I'm looking at the right code and can start dealing with it. And we've already talked about how to do this. This is why we need clear output. We need our unit tests to be clear and complete and unambiguous about what they found, where they found it, and what happened, right? That's really about making your unit tests precise. This is also why we organize unit tests carefully, so that if you find a failure in a unit test, it's easy to find the code responsible. Now, ordinarily, this is no big deal. I mean, if you've got a confusing unit test failure that you don't understand, but you've just rolled into the office at 10 or 11 o'clock or 1 in the afternoon or whatever, and you're just finishing up your latte, this is no big deal. You can go figure this out, right? We dig through code to see what's going on all the time. It's a different thing when it's 2 in the morning before the day you're supposed to cut a release, and something changed, no one knows what, and your unit test suite is failing and management is breathing down your neck to fix it. Or even worse, it's 2 in the morning after you cut a release, and all of your clients are bricked, and management is seriously breathing down your neck to figure out what's going wrong. Okay, you do not have to think very hard about a recent case where that was likely going on somewhere. All right? Under those circumstances, you really want clear, unambiguous, and non-confusing unit test output. All right, let's talk about accuracy. We'll spend a little bit more time on this. Again, accuracy is something about, are your unit tests giving you the right answer? And what that really means is that if your unit tests are failing, it's because there's really a bug, and if they're passing, it's because there really aren't any bugs. Remember that we're making a falsifiable hypothesis. My code has bugs, which we cannot prove true in general. I mean, the halting problem and all that, but just in real life, even simple programs are extremely difficult to absolutely prove true. So what we're trying to do is find the bugs. That's what we can do. And when we find one, that's a positive result. That's positive in the same sense that a COVID test comes back positive. That's not emotionally positive. I'm not saying you're happy about it, right? I'm saying the experiment has found the thing that you set the experiment up to find, right? That's a positive result. And what we don't want are false results. We don't want false positives, which are false alarms. There is no bug, but a unit test is failing, and you're going to waste a bunch of time and resources tracking it down. We don't want false negatives, which is where there is a bug, but it made it through your unit tests, and if it doesn't get caught somewhere else in your CI pipeline, it's going to make it out to production. And again, we have had recent examples of how much trouble that causes. So how do we make accurate unit tests? There's a lot we can talk about here. We're going to hit kind of the big three. We have to test completely, all right? If we're looking for bugs, we have to look in at every corner, under every stone, behind every bush, with a bright flashlight. Okay, we have to test our code completely. But we also have to test correctly, which is to say, we have to know what the right answer looks like. And we have to know what bugs look like. You might be looking right at it, but if it looks like it's supposed to be there, maybe you don't notice it's a bug. And then lastly, we have to make valid tests, right? We have to make falsifiable hypotheses that our code can actually use to find bugs. No circular logic. That happens much more commonly than you might think. So let's talk about this, how we test completely. Now, this is my favorite book on testing ever. It's a very thin book, published in '79. It is lovely to read. It is very entertainingly dated, right? The way that they were writing code back in 1979. But there is more good advice per page in this thing than any other book I've come across. And he's got very detailed, thorough discussions of how to completely test code. We're going to do the real informal version. Here's our code. Here we are. And what we've got down here is a number line. And we're looking at the domain of all the values that can go in, which is basically every value an integer can have. And we're going to look at all the execution paths through our code. You want to make sure, as a first step, that every execution path gets tested. So if we look at our code, there's a set of input values that make the conditional on line true, and we get the return value on line 2. And that's this stuff, right? All the positive integers, including 0, make the conditional on line 2 true. We just get back the thing we send in. And then all the values that make that false are down here, right? That goes from int min to 0, not counting 0. The formal term for these are equivalence classes, and the point is that if you test one value from an equivalence class, you have exercised that path through your code. You don't really have to go do another one. So on this basis, this is where we came up with that initial example. Pick one value from each equivalence class, make test cases or assertions for that, and you're good. You're not good. We're not done. But it's a good first step. Remember the first rule. Write unit tests. If you do no more than this, you're off to a heck of a good start. But there is something else we need to do, and that is we need to go check boundaries, edge cases, the interesting things in your code, which is where behavior changes. That's where subtle bugs can live, like typing less than versus less than or equal to, or off by 1 errors, or all that kind of stuff. Go examine those to see if you need extra test cases. Now, if we do that here, we'll work our way from the top down. We'll start with int max. If we send int max in, biggest possible integer, does anything special happen? The answer is no. the condition on line 2 is true. We just get that value back, nothing happens. We're not interested, we're good. What about 0? 0 might sound like an important number to test in absolute value, but actually, the way we've written it here, it's not. It just makes the conditional true like any other positive value, and you get 0 back. Big deal. All right, so let's look at our other equivalence class, and we'll start at the top. And if we put in -1, also nothing interesting happens. But if we put in int min, now you see that we have a problem. And the problem is that signed integers on every machine any of us are likely to see for the rest of our lives is asymmetric around 0. Whoops, here we go. The largest possible integer is positive 2,647,000,000, but the smallest signed 32-bit integer is negative 2,000,000,000 yada 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 648. If we pass this value into our function and we multiply it by -1, the result cannot be expressed in a 32-bit integer. This is signed integer overflow, and this is undefined behavior. Now, if you don't know about undefined behavior, let me scare you. Okay, so Ansel and Barbara gave a great talk several years ago, Back to Basics talk, so that's the Back to Basics gentle intro. Earlier, Chandler Carruth gave the not Back to Basics, but very thorough and grounded intro to this. And then Fedor comes back last year with half an hour of absolute nightmare. Okay, this last one is a great talk, but do not watch that alone in an empty house at night. Okay, I'm just saying. So the point is that int min is not a valid test case. It's not part of our equivalence class. There's no point in writing a unit test for that, because the only thing your program is going to do if you try it is misbehave. There is no defined behavior to test against. But what if we rewrite it? What if we change our code to check for that error case? Like, we'll put some code up front that says, if it's this value, well, the standard library is nice enough to give us a standard exception type called domain error. Let's throw one of those. All right? Now, calling the absolute value of int min is very well-defined behavior. It emits an exception. And so now this is a third equivalence class. Note it's also a third execution path, right? So now we have an extra test case. On line 4, we have the test case we had before. Now we have this additional test case on line 9. On line 10, we're using this nifty thing that Catch gives us. Again, unit test frameworks give us a lot of nice machinery. This executes the expression on line 11, and checks to make sure that it emits an exception specifically of the type on line 12. If you get a different kind of exception, or you don't get an exception at all, this test fails because your error handling code didn't do what it was supposed to do. Generally, by the way, error cases are separate test cases. Unit test frameworks go to great lengths to make sure that every test case executes in kind of a separate, independent environment, at least as much as it can. And hitting error cases tends to mess things up. So you want them sort of segregated off to the side so they don't mess up other tests. Okay, so that's a very quick view about how to test completely. Pete, quickly.
I have an awkward question.
Awkward question.
You said 0 is not a domain test case.
Yes.
All right?
Go ahead.
I pretend it is because if someone, for instance, leaves the less the equals off, the left the greater than and equals.
We will come back to that. So Pete's question is, he claims that 0 is an important test case that we ought to have because it's an easy mistake or something that someone might break later. There's actually several reasons we ought to have 0. We'll come back to that.
Just reinforce that. It's the difference between white box testing and black box testing.
I've got 10 minutes on that I was up late last night trying to figure out how to squeeze in. Yeah, white box versus black box. Oh, we will so get to that. Okay, briefly let's talk about testing correctly. We need to have an idea of what the right answer is, obviously, to write a unit test. So the point is, if I've got some extremely complicated and difficult mathematical computation, this being an extremely simple, very complicated mathematical operation that I can put up on a slide, how do I know what goes there? There's a lot of answers to that, okay? This is an area or a part of a larger issue called the test oracle problem, if you come across that term, which is more generally how do we come up with the right answers for more general testing problems. Now, the answer here is obvious. You can go to an external authority. We've known the right answer for a long time. There might be simple cases you can work out. There might be some known properties of the result. There's a whole area of testing called property-based testing that does this kind of thing. At the company I work at, we have whole teams of mathematicians and people who are experts on the phenomenology and the algorithms we use, and they go build prototypes in MATLAB or Python or something, get it to work, and then give that to the C++ developers to put into operation, right? So we go talk to the experts about what the right answers are, and we keep their stuff around. That's where we can get answers from. There's a lot of answers to the test oracle problem. My point is that you need to think about how you know what the correct result is and how you express it so that you don't build into your unit tests more information than you really need to. Whoops. Right. There we go. Now, valid tests. We need to avoid making tests that aren't actually testing anything. So one thing I don't want you to do is this. Do not put in as the right answer the thing you got by just running your code. All right? Don't do that. Also, don't do this either. Don't think to yourself, well, you know, I don't know what the right answer is, but I've got this nice code over here that computes it. Why don't I use that? All right? Don't do that. Okay? You have just written non-falsifiable unit tests. Okay? You're no longer doing good science. You're no longer doing good testing. I like Dave Farley's take on this. Congratulations, you have just proven that the code you wrote is the code you wrote. Now, I will just mention very briefly, it's not a unit test, but it might be useful. Things like this are frequently called acceptance tests. They don't prove your code is correct, but at least they prove that it does the same thing it did last time. And there are kind of difficult coding and testing situations where that's all you can do and that's all you can say. So this kind of thing does have a place in testing. It's not a unit test. Claire McRae has given several talks at CppCon and other places. She's done a whole lot of work in this and has got some open source tooling. So if you need to know more about acceptance tests, that's a really good place to start. All right, so let's wrap up this first part where we're talking about how we make unit tests that are good tests. We are doing science, and we're doing all the things that scientists do. We are very specifically making falsifiable hypotheses, and we've talked about at least kind of the big things you need in any good lab setup or a physics experiment, which is the same stuff we need. Now, we just covered a heck of a lot of material real fast. If you didn't get all that, or that seems overwhelming, or gee, I don't know if I can do that, that's fine. Because the first rule of unit testing is we write unit tests. Even if they're incomplete, even if they're imprecise, go write some anyway. It is almost never the case that a unit test ends up having negative value. All right, let's move on to the second big area that people will talk about and you get a lot of advice about, which is how do we make our unit tests good code? Now, there's a couple of things here. We need our code to be readable. We need our code to be maintainable. This thing about documentation is something we'll get to in a minute. I'm going to have to tell you what that's about. But let's start here. What does good code mean for unit tests? Look, we've got some complicated bunch of code that we're trying to test. We write unit tests to prove, not that it's right, but we're trying to prove it's wrong and we haven't yet. What do we do for our unit tests? If you like infinite recursion, you can write unit tests for your unit tests, but most people don't like to spend the rest of eternity doing that. So what do? We have to inspect our unit tests. The only way you can prove a unit test is correct is by inspecting it. Some human has to sit down and read this thing. That's the only good option. So if you're going to prove your unit test correct by inspection, it has to be very, very inspectable. Now, there's a tremendous amount we could say here, but the big thing is that they have to be simple. Going back to Dijkstra again, simplicity is a prerequisite for reliability. If your unit tests aren't simple, they're hard to inspect. I like John Jagger's take on this, and I apologize for not having a reference for this talk. Unit tests should have a cyclomatic complexity of 1. Cyclomatic complexity, there are tools that do this. They more or less measure how many code paths there are through your code. So that example we had before probably has a cyclomatic complexity of 2. You don't want your unit tests to have conditionals with big if blocks and logic in them, or loops, all right? If your unit test, if you stand back and look, right? You got, test case, whatever for your test framework, opening curly brace, and everything in the middle is indented the same amount, you're probably doing good. Because there's no ifs and there's no blocks and there's no nothing. Now, these are aspirational. I'm not saying there's never a time to have an if in your unit test. There are plenty of times to have an if. Sometimes you need loops. It's fine. We just aspire not to. My clicker is doing interesting things. There we go. Remember, I like this point from Girard. We're not writing our unit test for the CI/CD pipeline. I mean, at the time you might be. I want this damn pipeline to finish so I can check my thing in and go home. But that's not really who you're writing your unit test for. You're writing them for some other human. All right? The ultimate goal for readability in unit tests is this. Reviewers can tell if your unit tests are correct, even if they've never read the code under test and don't know what it's supposed to do. That sounds impossible. That is an extremely high bar. I'm not saying it's easy, but it's doable, and I'll show you how in just a minute. Now, we should move on. To talking about maintainability, but what we really have to do is loop all the way back and talk about something we skipped up front. How do we test classes? Now, from our original definition of unit testing, where we're testing on a function-by-function basis, you might think that you test your class by just testing the member function. And honestly, a lot of people do this. There is a better way. These two talks up at the top from Kevlin Henney opened my mind up to all kinds of possibilities. And I'm stealing this example straight from, I'm borrowing it from, he can have it back when I'm done. I'll, put gas in the gas tank and vacuum it. So this is a binary cup. It's either full or it's empty. The default constructor makes an empty one. You can see if it's empty or not. You can fill an empty cup. You can drink from a full cup. There's some air. You've written this code in your head already, right? This is the simplest thing we can test. Let's go try to test this. So what you might like to do if you're going to test this on a member function by member function level, you might think your test suite is going to look like this, right? One test case. Now, you might have more, right? We talked about how, error cases or separate test cases, that kind of thing. But at a minimum, you're going to have this much, right? So let's go try. Let's write that first one. Let's test the default constructor. We make a cup, and now what? Well, what you probably want to do is look into the internals of that object and see if it did the thing it's supposed to do. Which, of course, you can't do because this doesn't compile, because that's what private means. This is encapsulation, that's the point. So now what? So there's two ways out of this, which at first just look technical, but are in fact deeply philosophical and get right at kind of the core of what we're trying to do. Now, whoops. There we go. So this is the white box versus black box testing debate. White box testing is what we just tried to do. We're going to write our unit tests by looking at the internal state of some object via some trickery we'll talk about in a minute. All right, we're going to look at the internal state of the thing and see if it did what it was supposed to do. And then the question is, in C++, how do you do that? Black box testing, on the other hand, is where you are testing strictly by using the public member functions, and you're not going to look at the internals. But that's kind of a weird thing to do, so how does that work? We'll talk about that too. Now in C++, it seems like black box is our only option. You're not supposed to get to the private stuff of your objects, right? So kind of silly to talk about this. Other languages, this isn't true. Python, for example, has no private data. You do it either way. Across the entire software industry, everybody, almost everybody, will tell you over and over and over and over again you should do black box testing, even if you don't have to in the language. We'll see why in a minute. But let's go ahead and finish up this white box testing example. If you really want to do it, how do you do it? The answer is you add something down there on line 10. You're going to give your class a friend struct or something, typically a struct. Now, this cup tester thing doesn't get defined in your production code. It lives only in your unit tests, right? From starting on line 1 there in your unit test, you're going to make your cup tester, and it's a slightly weird thing. It's got a reference to a Boolean as a member variable. And then it sets that to refer to some cup that you pass it in the constructor. It's a little weird. Right? It makes sense if you kind of read it. But here's the point. Now you can do this. Your test case makes a new cup on line 8, makes a cup tester for it on line 9, and you use the cup tester to get to the internal state of your thing and see if it did what you wanted to do. White box testing. There's a lot of other ways to do this. This is the second half of a talk I gave a while back, talking in great detail about all the ways to do this and several ways to absolutely not ever go do this. Do not define private public at the top of your unit tests. All right, please don't do that. It's undefined behavior.
You have a bug in your slides.
Of course I have a bug in my slides. What's my bug?
Cup tester that is empty.
Yeah, why not? I think.
You called it is empty. The parameter.
Okay, yeah, typo, sorry. The principle holds, and there's a lot, by the way, I mean, seriously, there are a lot of different ways to use this friend thing to like get access to the internals, right? This is just kind of one simple way to do it. This kind of thing almost always works, is very applicable. It's kind of my preferred way to go do it. Advantages of white box testing is very commonly used. It is sometimes recommended. You have to say it's good for beginners. It's very obvious and straightforward what you're going to go do, right? So people who are new to unit testing, maybe you just want to try this up front. It's also really nice for testing edge cases or problems. If you've got access to the internals, you can reach into your object and sort of arrange all the gears and levers to be in an error case or to hit some particularly difficult problem, right? So it's easy to rig your objects for good tests. And sometimes it's your only option. If you're dealing with legacy code that doesn't have tests, you don't know what it does, you don't know how it does it, sometimes this is your only good option. The problem with it is it means your tests are very tightly coupled to your code. So, plus or minus typos, we'll see. So, line 10 in my code, I've got a private member variable named whatever its name, and the point is that that name is explicitly mentioned in my unit test. So if I refactor my code, I have to touch my unit test. I have doubled, at least, my maintenance burden for refactoring. If I change my code, I got to update my unit tests. Someone's got to go read the unit tests again. If you're in some areas, like, say, medical devices, or you're writing the code that runs the brakes in a car, there may be very serious regulatory issues involving having to prove that your unit tests are correct. And if you have to change your unit test code every time you rename a variable, you may have a problem. So what's the alternative? What's this black box thing that everybody says is so great? We test only using the public interface. So we do something like this. Here's our unit test. We make a cup. We call is empty. We're good. Now, this may bother people. If it doesn't bother you yet, let's write the unit test for the is empty member function, which there it is. And we've just written the same test twice, right? You have to have a cup with a known state. Test is empty. Why did we just write the same test twice? Because you cannot test these member functions independently. You need one to test the other. There's no way out of it. And of course, what worries people is that if you happen to have a bug in both of them, like your default constructor is making full cups, but is empty is returning is full, these will compile and run and you won't notice. Now what? Okay? I call this the black box conundrum. If you test only via the public interface, you have a circular logic problem. You can never tell that any given member function is correct in isolation. You can't isolate them. So what do? There is a way out of this, which is very interesting. The technique is from something called behavior-driven design, which is an offshoot of test-driven development, which we'll get to later. We're not going to talk about this much, except that we now take a fundamentally different approach to what we're doing. We no longer test member function by member function, which is what we've got here. These get replaced by unit tests for the behaviors we want. So our unit tests aren't about the default constructor or the isEmpty member function. They're about a new cup is empty. An empty cup can be filled. Drinking from a full cup makes it empty. All this stuff. What do you want it to do? So if we try to do this, some interesting things happen. First of all, we write the same code we had before. We make a new cup. We see if it's empty. That's the best we can do. If those two bugs are in there, this still passes. But when we try to test that an empty cup can be filled, this will fail because that cup isn't really empty, like we thought it was. In other words, Further tests of further behaviors will show that something is inconsistent. That's your signal that there's a bug. If the constructor was wrong, like we said, and isEmpty is wrong, and fill is wrong, but some other member function will show that there's an inconsistency. If every member function has got the internal state of this thing backwards, every behavior you test will come out right, and your code is correct. The implementation sucks. But we're not testing implementation quality. That's what your code reviews are for. You are all doing code reviews? Tell me you're all doing code reviews. All right, good, thank you. All right. Now, some very interesting things come out of this approach. Remember that we had that impossible ideal that we want our unit test to be correct by inspection, even for people who don't know what they do? Well, look, let's go back to our white box example. This is the white box example. I've expanded it so it's more readable. This thing where you got the cup tester with the isEmpty and the bool and all that stuff, and probably a typo. Consider the cognitive load on someone who comes in and reads this and has to figure out what's going on. It's not huge. We can figure this out. But contrast the cognitive load of reading this with the black box version, which says, a new cup should be empty. We make a cup, check it's empty. What else do you want? We have attained our readability goal by using only the public member functions and testing behaviors. We also get something else interesting out of it. You can get this out of white box testing too. It's not only black box testing. This behavior-driven development steers you strongly in this direction. Here's a more complicated test case. We want to test that drinking from a full cup makes it empty. So given, behavior-driven development uses this structure, given, when, then, uses that all the time. We make a cup, we make sure it's full, we drink from it, we check the success, and we make sure that now it's empty. Not only does the name of the test document the requirements that we were given when we wrote this thing, so our unit tests now document the desired behavior, but the unit tests show you how to do it. These are your examples. This is the documentation for people of how to use your thing. If you're doing black box behavior-driven development, this tends to show up on its own. Doing this in white box testing is much more difficult. So, what's the downside of black box? It's only possible if the public interface is well designed to let you do this, and that is a very big if. Most code out there is not well designed to do this. So it's difficult to do in practice. We need to revisit our definitions. For white box testing, our original definition is fine. We test at the function level. Black box testing means we are no longer testing functions. The smallest unit of thing that we can test is now behaviors of functions of classes. We can also go back and clean up something. Remember back when I first put this up, I said a test case tests one thing, which was kind of ill-defined at the time. Test cases actually test one behavior. That's the idea behind a test case. It's one behavior of the system under test. So let's wrap up all this business about what it means for unit tests to be good code. With a suitable helping of white box versus black box philosophy, we need our code to be readable, simple, cyclomatic complexity of 1. We didn't have time to go into telling a story, but that given, when, then tends to steer you towards writing code that has the same 3-act structure as good fiction, which helps people read it. Pete, quickly.
So with a class, the public interface is the stuff you're supposed to be keeping roughly the same, to be adding to it, which is why if you start using white box testing, you've now frozen the private implementation.
Yes.
The whole philosophy behind classes is that private implementation can be changed.
Yes. Right. So, yes.
Derail that part of the design.
Yes. So when you're designing, so this comes back to design, which we will get to shortly, very briefly. The idea behind well-written code, well-designed code, is that the public interface doesn't change much and the behaviors don't change much. If the behaviors change, you have to revamp your unit test, but what do you expect, right? But the point being is that you need to be able to modify and update your code and refactor your code, improve the structure and all that stuff, ideally without breaking your unit test. If you're doing white box testing, your unit tests are trying to freeze your implementation, which can be a big problem. Black box testing freezes only the public interface, which hopefully doesn't change much, and the behaviors. And even then, only that you can't take something away. You can add behaviors and everything's fine. Okay. We just covered an enormous amount of stuff. This white box, black box thing is deep. What's the first rule of unit testing? Write unit tests. Thank you very much. Even if you can't do all that, go write unit tests. All right. We don't have a lot of time left. We've just got a couple of more things to put in. I mentioned that there's this kind of fuzzy thing about good process. Unit tests must support good processes for software development. Good software development processes should support unit testing. We've only got time to really talk about two things here. We're going to mention design, which you just asked about, and then test-driven development is the 800-pound gorilla in the room. There we go. Here's the point about design. Now, by the way, there is a whole conference track about software design and architecture. If you go to that, I don't know what they're talking about, but back in the old days, youngsters, you talk about software design and there's this big long list of things you're supposed to do. Simplicity, small functions, single responsibility rules, solid principles, open, closed, and testability is in there somewhere, usually down near the bottom. If there's anything we have learned over the past 2 decades, as we have evolved our ability to test our software and understood how damn important it is, we now know something. Testability isn't in this list. It is the list. Everything you do to write good software makes it testable. Everything you do to make software testable makes the design better. This is surprising. A team I was on many years ago learned this the hard way. We finally refactored something to make it more testable, and it made so many things better. And every time we did it, we saw the same thing, and it was amazing how much better our code got just by making it testable. We were surprised. So was everybody else. Hopefully Jody talks about this afternoon. He's got that talk. Oops. So briefly, when pragmatic programmer Andrew Hunt and David Thomas tell us to test early, test often, and test automatically, there's a lot of reasons for that, some of which we'll get to in a minute. But part of that is we want to test as we go because our unit tests will improve our design. If your code is hard to test, it's because the interface is bad, particularly if you're doing black box testing. Your interface is bad for your users too, because you can't get it to do stuff. So unit testing improves your design as you go. All right, let's finish up with test-driven development. This is a huge, huge, huge area of software development. Kent Beck developed this as part of his extreme programming stuff back in the late 90s. I believe this is the first book where he talked about this. Phil Nash gives a lot of classes on test-driven development. He lent me this slide. Again, I'll dust it off before I give it back to him. You will hear about the red-green cycle, where first you write a test that fails, and then you make the test pass. So what's going on here is that you start off by looking at what you need to do, and you choose the smallest chunk of the thing you need to invent or build. It doesn't all monitor. You pick off the smallest amount of functionality you don't have yet. You write a unit test for that, which fails because you haven't written it yet. That's the point. Then you put on your hacker hat and you write code as quickly as possible, minimal code, to get to the point where your unit tests pass. Make it go green. Then you switch hats and you become an engineer and you say, all right, this code is horrible. I'm going to make it clean. So now you refactor. Note, while you're refactoring, you've got a unit test that's green to tell you if you goof. By definition, refactoring means you're changing the structure of the code without changing the behavior. Once you've refactored and you're happy, are we done? Great, you're done. If you're not done, you go back around, choose the next smallest chunk of work to pick off, write a failing unit test for that, rinse and repeat. Now, this cycle has to go fast. Ideally, this takes less than a minute, maybe only 20 seconds sometimes to go through all this stuff. Which is why one of the things you keep hearing is that CI/CD pipelines and all this stuff, but particularly running unit tests, has to be fast. Seconds to run unit tests, not minutes.
No sleep.
Yeah, unit testing thread-safe code is all kinds of fun. We are not talking about that at a back to basics track. This constant switching between mindsets is interesting and strange at first. It's really good practice for people. This isn't as easy as it looks. This requires a new set of habits and it needs practice, and most people who don't like it are people who tried it and just couldn't get it to work. But look, again, this is a quip from Dijkstra from way back. If debugging is the process of taking the bugs out, programming must have been where you put them in, right? Test-driven development, writing the test first, give them no place to leave. They can't get in the first place because if it's wrong, your unit test failed. And they failed to begin with. Also, I didn't mention this forces that black box design business. If you can't test it, you can't write it, which means your design has to be sort of good to go anywhere. It really forces you to black box good design interfaces. Anyway, it keeps the bugs out. It does some other interesting things. I like this comment by Kevlin. Don't think about writing the test first. You're specifying the desired behavior first. You are first starting by writing in code what your requirements really mean. This is a tremendous change in how you approach coding. Now, a couple of years ago, Fedora gave a back to basics on test-driven development. And I love this comment. It's not about what it does to your code, it's what it does to your mind. Now, if I'm the guy putting science into unit tests, it sounds like Fedora is trying to start a religion. And I'm signing up, okay, because he is absolutely right. It does. All of this changes your approach to software development in very fundamental and interesting ways. You cannot throw a brick on the internet without hitting something about test-driven development or a video about cats. But just as a place to start, Phil has given any number of talks at conferences about test-driven development, frequently using the catch framework that we were using. This is a link to Fedora's talk from a couple of years ago. Very interesting talk. Kent Beck is still blogging about this, and so is everybody else. All right. So let's wrap this up. Good process. We mentioned design, and that unit testing improves design, and good design is necessary for good unit testing. And this whole test-driven development thing, which again is, I mean, there's a whole industry about talking about this. It's got a lot of very surprising benefits, which aren't obvious up front, but it needs practice. It needs developing a new set of habits. So take some classes, get a mentor, all right? It isn't as easy to do as it looks. Oops. So we've spent almost an hour, we're almost out of time, taking this grand view across the big three areas of unit testing. We need good tests, we need good code, and this has to work into the way that we develop code and do our jobs. Good tests are science, replicable, repeatable, accurate, precise, falsifiable. Good code is about readable and maintainable. Ideally, we get some good documentation out of that, particularly if you're doing the black box thing, really pushes you in that direction, which is valuable. Good process is things like your unit tests improve your design affects how you write your unit tests, and this whole test-driven development thing. And this whole thing with this big side helping of white box, black box philosophy. So to wrap up, let's go back to Karl Popper, way back in the 1930s, when physics had to go rethink what it was about. Good tests kill flawed theories. We remain alive to guess again. It's a good quip. When we're talking about software testing, it's got a little bit more of a bite. Good tests kill bugs. We remain alive to compile again.
Or employed.
What's that?
Remain employed to compile again.
Yeah, if we don't kill all the bugs, maybe we remain employed. Maybe we have to reconsider some choices we've made in our lives. But bad tests are still better than none. You'll kill some of the bugs. What we know now, again, is that lack of testing kills projects, sometimes kills companies. The 90s, in particular, you go back and look, it is littered with the smoking wrecks of companies that did not develop code properly. And we still have those problems. Recent, very, very large and visible and public problems, right? You go read about software failures that cause problems, it's a very grim reading indeed. And what we know is if you're not testing, you do have bugs. It's guaranteed, and they're going to get out into production. So, what's the first rule of unit testing? Write unit tests. What I want you to do is go write some unit tests and kill some of those bugs. Thank you. We have 30 seconds. We have 30 seconds for questions, or really 20. I'm a senior developer at SciTech. I'm in charge of the biggest project we've ever had. We are a defense contractor. We are seriously hiring. We've got a booth out here. Come talk to us. I will be around all week. And some of you who know me know that if you ask me about unit tests, you can't shut me up. We have 10 seconds. Yes, sir.
If you go look at the poster on standard interval and look at the code behind it, the test code's all written in Catch 2, and it runs around 36,000 test cases, which are combinatorially generated. If you want to see what it looks like in full flower, there's example code you can go look at.
Right. So there's a
QR code on the poster.
right. So for the video, there's a poster in the conference that does all the stuff we just talked about. I didn't get to look at it last night. We'll go look. Thank you all very much. Thank you for coming.